You're running airport security with 2 screening lines. Each one has a loading area where several people can prepare at once, but only one bag can be screened at a time. How do those 2 steps work together? Where does the bottleneck form? And does adding more space to load bags actually speed things up? There's a model for that. Welcome to Model Monday, a series where we break down scenarios in different industries, organizations, and departments and explain how you can build a simulation of them in Process Playground. Let's model it. Let's drag out the demand block that will start this process. Then we'll open up our item types window to set up the items. In this case, we just have one and we'll call this passengers. Then we'll open up this demand block and we'll set the time between arrivals to an exponential distribution with a mean of 0.23 minutes, so about one person arriving every 14 seconds, or about 261 people an hour. Then all of these passengers will go into a common queue, so we'll create that and then we'll rename that here. Now, let's say at the time the line opens, we already have 30 people waiting in line. This is where our initial on-hand parameter comes in. We first have to add the passenger's item to the queue block in order to find this parameter, and then we'll see an initial on-hand option, which we will set to 30, to indicate that we want 30 people in line at the beginning of the simulation. Once you get to the front of the common queue, there are 2 different lines to go down. Let's build out the first one. We will take out a queue block and rename this lane queue, and this queue represents the space waiting right before you put your bags on the conveyor belt. So to indicate the constrained space, we're going to have a max items of 2. Then we'll start loading the conveyor belt. We will indicate this with an activity block, and we'll call it load belt. There are 4 spaces where people can load their bags, so we'll set the servers available to 4. Let's put in the processing time of a triangular distribution where the minimum time is 0.2, the mode is about half a minute, so 0.5, and 1 minute is the max loading time for each passenger. Then we can screen the luggage. The screening will be a bit faster, but there's only one screening machine. So we'll pull out the activity block and we'll call this screen luggage. And then the processing time here will be a triangular distribution with a minimum of 0.2 minutes, then a mode of 0.4 minutes, and then 0.7 at the max. Great, and now we'll let the luggage out. So we'll create an exit block and connect this up, and then our passengers will go on their way. Now we're going to make a copy of all this, either by using shift-click in drag in pan mode, or clicking and dragging in select mode, and dragging across to select multiple shapes. Then we will copy, Control-C, and paste with Control-V and bring that down here. All of the parameters we've already set will also be copied, so we just need to hook it all up. We should be ready to run and see what happens. Let's run this for 100 minutes. Notice in this common queue we had 30 people in line, but it's already gone down a little bit. You can see in these 2 queues that they never get above 2 people. In the activity block, we never get above 4, and then in the screen luggage block, we never get above 1. So everything about how we expect this model to run is running smoothly. Let's take a look at our results. For our exit block, we see that in this block, we had 235 passengers move through the process, and we also like to look at our total lead time in exit blocks, since it indicates the time the passengers entered to when they finished. We're going to apply that to all exit blocks. And then we're going to look at loading the belt in this activity block. We care about our block cycle time, so we want to make sure that that matches what our original distribution looked at. But particular for our activity blocks, we care about our runtime, our idle time, and our blocked time. And we'll apply that to all 4 of our activity blocks. The runtime indicates the percentage of the simulation that the activity block was actively working on items. The idle time is the percentage of time that the activity block was waiting for items to work on. And the blocked time tells us the percentage of time that the activity block had completed processing an item that it was working on, but could not pass the item on to the next block. We can see that the loading belt was only active about a third of the time, But that was because we were blocked by the screening machine. And we definitely experience that when we're standing in line at the airport. We can see for the most part, the luggage screening process was running constantly. Now let's take a look at our queues. We're going to add our count and our max here, and then we'll go down to this other block. We'll also do count and max. And now let's take a look at our common queue. We saw that we had processed 438 passengers over the course of the simulation. And then we can look at this queue length graph. It shows our initial 30 passengers, and we had kind of a bit of a surge at the beginning, but eventually our process worked through it and it was able to keep up well. So in a nutshell, that's the airport security model. But the real value is in what you can experiment with. By modeling each line as a combination of steps with different capacities, like loading the belt and screening luggage, you can see where the true bottleneck forms and how it affects the entire process. And it's not just security lines. The same pattern shows up in grocery checkout with bagging and scanning, manufacturing lines with staging and processing steps, or any system where work moves through multiple stages with different capacities. From here, you can start to ask real design questions. Should I increase capacity at the loading step or the screening step? Does adding more space upstream actually help, or just create a larger queue? What happens when demand increases? Those are the kinds of trade-offs this model is built to explore. That's the model. Now go experiment. Happy modeling!